Hello everyone. Today is the second lecture of fluid mechanics in the online lecture series of fluid mechanics, and our topic of discussion for today will be the analysis of mechanical behavior of fluids. So how to analyze the mechanical behavior of fluids? The most fundamental approach will be the analysis of dynamics of individual molecules using the equations of motion. So to analyze any fluids, we may use this approach by analyzing the dynamics of individual molecules using the equations of motion. Now this may sound quite simple and appealing, but there are certain physical constraints that are associated with this. To understand it, let us consider a certain molar volume of a fluid, be a liquid or a gas. So we are considering a certain molar volume of a fluid. Now at normal temperature and pressure, according to Avogadro's law, even for a certain molar volume of fluid, it will contain 6.023 into 10 raised to the power 23 molecules. So our fluid which we have considered contains 6.023 into 10 raised to the power 23 molecules, and each molecule is undergoing both translatory motion and rotational motion. So it is translating, there is translation as well as rotation. Now the translatory motion is described in terms of the translational velocities which a fluid molecules undergoes along the three mutually perpendicular axes. So let us say that these are the three mutually perpendicular axes along which a fluid molecule is translating. Let us say that this is x-axis, this is y-axis, and this is z-axis. So any fluid molecule is translating along the three mutually perpendicular axes, and let us say that along the x-axis it is moving with velocity u, along the y-axis moving with velocity v, and along the z-axis w. So the translation is described by using three components. The three components of translational velocity. Now, along with translation, a fluid molecule is also undergoing rotation. So the rotation of fluid molecule will be about the three axes which we have considered. It may rotate. It is rotating about the x-axis. Let us say that the rotation be denoted by omega x, about the y-axis omega y, and about the z-axis omega z. So along with the three translational velocity components, we have three rotational components. Now this is for one individual molecule. So we have three translational components, three rotational components. So the motion of one individual molecule requires 6 variables. Or you can say that the motion will be described by using 6 equations of motion. But the molar volume which we have considered, it contains how many molecules? It contains 6.023 into 10 raised to the power 23 molecules. Each molecule having 6 equations of motion. So overall, how many equations of motions we need to consider? We will multiply this by 6. Now this figure is quite very large. for a smaller molar volume which we have considered. So analyzing this large number of equations of motions, this is quite impractical. Even though today we have advanced computational technology, but still this analysis will be very impractical and inconvenient. Now, how to deal with this situation? To deal with this situation, we need to reduce the number of variables. The number of variables will be reduced by using a different approach. So to deal with this situation, we have two individual approaches, which is the two approaches are known as, first is microscopic approach and the second is macroscopic approach. Now let us understand both these approaches so as to get a greater picture of the so we have two approaches to deal with the situation. First is the microscopic approach and the second is macroscopic approach. Now what is this microscopic approach? The first approach, it concerns with dealing with statistically averaged behavior of many molecules constituting the matter under investigation. So what we are going to do here, we will deal with statistically average behavior. We are going to deal with statistically average behavior of many molecules that constitutes the matter which is under investigation. This is what is known as microscopic approach, where we primarily focus on the average behavior of individual microscopic constituents of matter. These examples include kinetic theory of gases, and statistical mechanics. The second approach is the macroscopic approach, wherein the number of variables are further reduced by considering the gross effect of many molecules, which can be which you can say which can be perceived by our senses and which can be measured by using any measuring instrument. To understand the difference between both the microscopic approach and macroscopic approach, let us try to see about pressure from both these points of view. So let us now see pressure from both the point of views, both the microscopic approach and the macroscopic approach. Now, on the basis of microscopic approach, pressure originates due to the rate of change of momentum of the molecules due to collision. Whereas in macroscopic approach, pressure is described in terms of the time averaged force over a given area that can be measured by using any pressure gauge. So in macroscopic point of view, pressure originates due to the rate of change of momentum of the molecules due to collision, due to the continuous collision which the fluid molecules are undergoing. And in the macroscopic approach, as I have said, pressure is described in terms of the time averaged force over a given area. So here we have time averaged force over a given area. Now, in macroscopic approach, this can be measured by using any pressure measuring instrument, let us say pressure gauge. So it can be measured by using pressure gauge. So it is quite clear that the macroscopic, in case of macroscopic approach, we will get a fewer number of variables. fewer number of variables to deal with. So now the question arises, is the macroscopic approach suitable for fluid mechanics, for studying fluid mechanics? See, in fluid mechanics, this macroscopic approach also have certain constraints. Uh, Suppose we are interested in computing the density of a fluid medium. Density, you know about density. Density is defined as the mass per unit volume. We denote a density as rho, and it is defined as mass per unit volume. Now, if we know the number of molecules, how to calculate this mass? This mass may be calculated by the number of molecules into the molecular mass. So if we know the number of molecules, we can easily calculate mass, and for a given volume, we can easily calculate the density of fluid. But we know that in case of fluids, the molecules are in constant motion. They are continuously moving from one place to another place, and that too in a random manner. Now, if we consider a very small elementary volume, what will happen? It will contain few number of molecules. Now, if we consider a sufficiently large volume of fluid system of a fluid, then it will contain larger number of molecules. So, how to measure density in that case? In case of smaller molecular, in case of a small molar volume, if the number of molecules will be less, we will get a different density of the fluid. For the same fluid, if we consider a larger volume, the number of molecules will be more, and obviously we will get a different value of density. But this is not true, because the density of a fluid is constant, or rather it is very, it every fluid has a specific density under certain, under conditions of temperature and pressure.